Hello and welcome to my science tutorials. In today's video we are going to be looking at what born-Haber cycle. So without further ado, let's get started. So a quick introduction to what a born-Haber cycle is. So in the formation of an ionic molecule or a compound, okay, for instance sodium chloride, if you want to form sodium chloride, okay, there is an amount of energy that we need to form sodium chloride, okay, by adding sodium ion and then chlorine anion to form the sodium chloride as the solid that we have over here, okay. And then that energy is what we call the enthalpy of formation of sodium chloride, okay. Now there are many factors and steps contributing to the overall enthalpy of formation of a particular compound, okay. Some of these factors include the ionization energy of the compounds, the electron affinity, enthalpy of dissociation, enthalpy of sublimation or enthalpy of atomization, and then the lattice energy. Now these energies are very crucial because once we know these various energies, we can be able to sum them with the lattice energy to get our enthalpy of formation of any particular compound that we are given. So I made mention of some various factors. So I assume over here you know what ionization energy is, you know what electron affinity is. So we are going to look at what enthalpy of what dissociation is before we look at what the born-Haber cycle of the compounds look like. So we have enthalpy of what dissociation, enthalpy of dissociation, okay, represented by what? Delta H diss to show the dissociation. Now the enthalpy of dissociation, this is the energy required, okay, to break 1 mole of a covalent bond to its separate isolated gaseous species, okay. So assuming we have chlorine, which is chlorine gas, okay, and we want to have just chlorine molecule, just chlorine atom, sorry. So we have 2 moles of chlorine gas over here, okay. The amount of energy we need to break this bond, which is what? Chlorine and then chlorine over here, to form what? 2 moles of this chlorine gas, okay. The amount of the energy that we need to do this is what we call the enthalpy of dissociation, okay, because we are breaking a bond, so it's the enthalpy of dissociation of this compound. Now mind you, this is really affected assuming we have any coefficient over here, okay, any coefficient over here before we do the dissociation. That coefficient also affects the enthalpy of dissociation. We get to look at an example of what I mean. So the second one we want to look at is what? The enthalpy of what? Atomization, which we represent by delta H atom, okay. Now the enthalpy of atomization is the energy required to convert an element in its standard state to 1 mole of what? Its gaseous state. So what do I mean by this? Maybe we have sodium, okay, solid, and we want to convert it to what? Sodium gas, okay. The amount of energy we need to do this is what we call enthalpy of what? Atomization, or the enthalpy of what? Sublimation. Enthalpy of sublimation. So this is the amount of energy we need to convert a solid to its gaseous state, an atom from its solid state to its gaseous state. So that is what the enthalpy of atomization or sublimation does. Now the last one we want to look at before we look at the born-Haber cycles of some various compounds is what we call the lattice energy. So the lattice energy is the energy evolved when 1 mole of what? An ionic crystal is formed. So the energy involved, okay, in combining sodium ion and then chlorine anion to form sodium chloride, okay, the energy in just adding the 2 of them is what we call the lattice energy of sodium chloride. Now a combination of the lattice energy, the enthalpy of atomization, enthalpy of dissociation, and the electron affinity, and then what? The ionization energy of the various elements that form a particular compound or ionic compound gives us the overall energy of formation of that compound, which is what we are referring to as the enthalpy of formation of a particular compound. Now let's have a look at what I mean by this. So the first one we want to look at is the born-Haber cycle. born-Haber cycle of sodium chloride. Cycle of what? Sodium chloride. Okay, so the equation goes like this. So we have sodium, which is solid, plus chlorine. Okay, so we have chlorine, which is half moles of chlorine, to give us what? Sodium chloride, which is what? Solid. This is gas. Okay, so the amount of energy needed to do this is the enthalpy of formation. Now mind you, because the product over here is just sodium chloride, so the chlorine molecule, which is gas over here, we need half mole of it so that we get just one chlorine. Now for us to form an ionic compound, we need the atoms in what? Their ionic states. So we need to do the conversion from the solid state, or either the solid or the gaseous state, to its ionic state before we can form the compound. So what we need to do first is to first convert the sodium to what? To its gaseous state, and then from here we convert it to what? Its ionic state. Okay, this is plus. Okay, then this as well, we need to first of all convert it to just chlorine gas. Okay, and then we convert this to what? Its anion. Then we add the two molecules to give what? The sodium chloride that we have over here. Now, as I explained earlier on, in converting an atom from its solid state to what? Its gaseous state, you need an amount of energy that we call what? The enthalpy of atomization or sublimation. The enthalpy of what? Atomization, or the enthalpy of sublimation, or enthalpy of what? Sublimation. Okay, so this is the amount of energy that you need to convert an element in its solid state to its gaseous state. Now applying this energy, we now have our sodium in its what? Gaseous state. So we need to now convert it to its what? Ionic state. So to convert sodium to sodium plus, we need to remove an electron from its valence electron. So we can remove this by applying what? Ionization energy to the sodium in its gaseous state. So once we apply the ionization energy, we tend to get our sodium plus as what we want before we can form our molecule. Now for the chlorine, we need to first of all break the covalent bond between the two chlorine molecules to get just the chlorine gas before we do the ionization, before we convert it to its ion. So the amount of energy needed to break the covalent bond between the chlorine molecule, as I said, is what? The enthalpy of what? Dissociation. Okay, but then because we have half over here, the enthalpy is also affected by the coefficient of the molecule that we have over here. So you need half the enthalpy of dissociation to form the chlorine gas over here. Now after we have the chlorine gas over here, we need to what? Add one electron to the valence electron of the chlorine for us to get what? The chlorine as what? An anion. So for us to do this, the chlorine, we have to apply what? Electron affinity. That is the energy we need. So the electron affinity of chlorine, okay, if it is high, then it can what? Pull an electron from another atom that does not that wants to be stable, and then therefore tends to lose an electron. The chlorine will now pull the electron into its outermost electron, its outermost shell, for it to have what? Chlorine minus. Okay, so we need electron affinity. Now in adding the chlorine plus the chlorine anion, the sodium plus the chlorine, the amount of energy involved in adding the two of them to get the sodium chloride is what we call the lattice energy, Le over here. So for us to get the overall enthalpy of formation of sodium chloride, the enthalpy of formation of sodium chloride, all we need to do is first of all add the enthalpy of atomization of what? Sodium, the ionization energy of sodium, the enthalpy of dissociation of what? Chlorine, the electron affinity of what? Of chlorine, the lattice energy of the two ions to form the sodium chloride, and then the sum of all of them will give us what? The enthalpy of formation of sodium chloride. So let's go. So we have enthalpy of what? Atomization. Mind you, I said this or this, so you don't need to write the two of them, so just one of them will do. Then plus the ionization energy of the sodium, then plus half the enthalpy of what? Dissociation of what? The chlorine, then plus the electron affinity of what the chlorine, then plus the lattice energy. Okay, so once we add all of this, we get the enthalpy of formation of sodium chloride. So that is how the born-Haber cycle of sodium chloride looks like. So let's look at the born-Haber cycle of another molecule, and then we solve some few examples, and then we end the tutorial. So the born-Haber cycle for what? Magnesium oxide, which is solid. Sorry for my terrible handwriting over here. So we have magnesium, which is solid. Let me pull this up a little because this is going to be mean. So we have magnesium solid. Okay, then we add what? Oxygen to it. We know oxygen, it comes as a gas, so oxygen gas, so we just need one so that we form this. So if we add the two of these, we get magnesium oxide, which is solid. So we need enthalpy of what? Formation. This is the amount of energy that we'll be needing to form this. All right, now as usual, this is magnesium and it is in its solid state. So first of all, we need to change it to its gaseous state. So magnesium, we need to have magnesium in its gaseous state. Now mind you, magnesium, this, if you write the ionic equation of this, you get magnesium 2 plus what? Oxygen 2 minus. Okay, before you can be able to get this molecule. So we need to what? Make sure we get magnesium to have the power of what? The charge of what? +2, and then the oxygen, the charge of what? -2, for us to get what we want at the end. So we need to first change the magnesium from solid to its gaseous state. Then we need to change from the gaseous state to its ionic state, which is +1, and then from there we change it to have the charge of what? +2. The same thing happens with the oxygen. It is in its gaseous state, but we need to just have what? Oxygen in its gaseous state. Then we change it to oxygen with a charge, which is an anion. Okay, then we further change it to what? Oxygen to have 2 minus. Okay, then we just add these two, okay, to give us what we want over here. Now in changing magnesium solid to magnesium gaseous, we know we need the energy we call enthalpy of what? Sublimation, okay, or atomization. Enthalpy of sublimation or atomization. Okay, now if we apply this, we get magnesium in its gaseous state. So we need to do what? Apply the first ionization energy to this. So the first ionization energy will give us what? Magnesium plus. And then if we apply the second ionization energy, okay, it will give us what? Magnesium 2 plus over here. So we need, first of all, we need the enthalpy of sublimation to get magnesium gas. Then we apply the first ionization energy to give us magnesium plus, and the second ionization energy to give us what? Magnesium 2 plus. Now for the oxygen, we need to break the covalent bond between the two oxygen atoms. So we need what? Half the enthalpy of what? Enthalpy of what? Dissociation. Okay, mind you, the half is from here. Okay, so assuming we don't have any half over here, depending on the compound that you are dealing with, then the coefficient half should not be here. It's not always the case that the half is here. No, look at what the balance equation you have at the top is, and then you go accordingly. Now after we apply the enthalpy of what? Dissociation, we get the oxygen just in its gaseous state. Now we need to apply what? Electron affinity, which is what? The first electron affinity to it. Then we get O minus. Then we apply the second electron affinity, then we get what? O2 minus. And then we now combine this and this using what? The lattice energy to get our answer, or what we want, the product that we want. So the enthalpy of formation of this particular compound, delta HF, is equal to what? The enthalpy of what? Sublimation plus the ionization energy, the first ionization energy, plus the second ionization energy, plus the enthalpy of dissociation of oxygen, the ionization energy, the electron affinity, of this molecule, then the electron affinity, the second electron affinity, then plus the lattice energy will give us what? The enthalpy of formation of the molecule. So let's go ahead. We have delta H of what? Sublimation, plus first ionization energy plus second ionization energy. Let me just put second over here to differentiate it. Then plus half enthalpy of what? Dissociation. Then plus what? Electron affinity 1 plus electron affinity 2. Okay, then plus lattice energy. Okay, so this will give us what? The enthalpy of formation of magnesium oxide. And then it goes on. Once the compound is an ionic compound, you just need to write the general ionic equation for forming the compound, and then you try to break the elements down till you get their ionic forms, and then you add the two ionic forms to give you the product, and you need lattice energy to do that. And then you add the various energies that are involved in converting from either the solid state to its gaseous state, and further from the gaseous state to its ionic state. And then you add all of the energies, and then you get your enthalpy of formation of this particular compound that you are interested in. So let's look at some few examples. Example number 1. So we have to write equations for the following processes. So enthalpy of formation of magnesium chloride, and then the value is what? Negative 642 kilojoules per mole. So which means this reaction is exothermic. And then we have sublimation. The enthalpy of sublimation of magnesium is 150 kilojoules per mole. The dissociation energy of chlorine, the enthalpy of dissociation is 244 kilojoules. First ionization of magnesium is 736. Second ionization energy is what? 1450. Electron affinity is what? Negative 348 kilojoules per mole. And then the second part is telling us to draw the energy cycle linking the above data, and hence find the lattice energy of magnesium chloride. So let's get started. So let's answer the first part of the question. You see, you have to write equations for the following processes. So for the enthalpy of formation of magnesium chloride, this is very simple. We just need to write the ionic equation for just need to write the general equation for forming what? Magnesium chloride. So if you want to form magnesium chloride, we need what? Magnesium solid plus chlorine gas, okay, to give us what? Magnesium chloride. Okay, so as a solid. So the enthalpy of formation of this compound as given over here is what? Negative 642 kilojoules per mole. So that is what all that the question is asking us to do. That is for the first part. Now the sublimation of magnesium. So we have magnesium solid, okay, magnesium. Then we are changing the magnesium solid to what? Magnesium gas. Okay, so we need enthalpy of what? Sublimation. Enthalpy of what? Sublimation, and that is what? 150 kilojoules per mole. Okay, so the dissociation of chlorine. So we have chlorine molecule, which is gas, to what? 2 moles of what? Chlorine. Okay, so enthalpy of what? Dissociation is what? 2, 4, 4. I mean, you get it. So you just write the various equation for this. The ionization energy, that is this. Let's go. So the ionization energy will be what? For first ionization energy for magnesium. So we have magnesium giving me what? Magnesium plus. Okay, so magnesium gaseous giving me magnesium gaseous plus. Okay, then you write the enthalpy, which is what we have over here, 736. So there again, we have the second ionization energy. It will still be the same, but here will be what? 2 plus, and then you change the energy. And then we have what? The electron affinity of chlorine. So we have chlorine gas, okay, plus an electron, will give you what? Chlorine anion. Okay, then you write its answer over here. Now the magnesium, this we need to balance the charge, so plus electron over here, so this will balance this. So this is the first aspect of what we have over here. Now the second aspect of the question is telling us to draw the energy cycle linking the above data. That is what we call the born-Haber cycle for this particular molecule. So let's go ahead and do that. So the born-Haber cycle of magnesium chloride. Okay, so if you want to write the born-Haber cycle of magnesium chloride, so let's have magnesium chloride over here. So we have magnesium, which is what? Solid, plus chlorine, or magnesium chloride, chlorine, which is also in its gaseous state. To form, this is the enthalpy of formation. Okay, then we have what? Magnesium chloride as the molecule. So first of all, we need to change this to what? Magnesium gas. Okay, and then we change it to what? Magnesium plus, and then from magnesium plus to what? Magnesium 2 plus. And then from here, this, because we do not we need the 2 mole of the chlorine molecule itself, so we don't need to break it down, we just need to what? Convert it. So we apply what? The first ionization energy to this. So we have the first ionization energy, sorry, electron affinity. Okay, because it's 2 molecules, so we just apply 2 molecule of electron affinity for this. So first of all, let's convert it to its atom. So we have chlorine gas. Okay, so we have 2 mole of the chlorine gas over here. Okay, and then we now use what? We convert from 2 mole of chlorine over here, we apply what? 2 electron affinity over here to give us what? 2 mole of what? Chlorine anion, and then we add the 2 of them to give us what? The magnesium chloride over here. So we need what? The lattice energy. So the overall equation for the enthalpy of formation for this is what? First of all, we need what? The enthalpy of what? Sublimation of what? The magnesium, which is what we have over. Oh, sorry, I didn't do this. So first of all, from this to this, we need the enthalpy of what? Sublimation. Okay, then from here it will give us this. From here we need ionization energy, the first ionization energy. Here we need the second ionization energy. Here we need what? The enthalpy of dissociation of chlorine. Okay, so we need the enthalpy of what? Dissociation of what? Chlorine. And let's see, what do we have? Enthalpy of dissociation of chlorine. So exactly, so we need the enthalpy of dissociation of chlorine, and then we need what? The electron affinity, twice that, to give us this. So we have this, which is this, plus what? The electron affinity 1 plus what? Electron affinity 2, electron affinity 2, then plus the enthalpy of what? Dissociation plus what? Twice the electron affinity. Okay, then plus the lattice energy. So once we add these individual energies, then we get the answer that we want. So let me get rid of this. I hope you've copied the equations down. So let me quickly pull this up. Okay, so we have to find what? The lattice energy for this. Now the question is telling us the enthalpy of formation, which is this, is what? Negative what? 642. So it's equal to, now we have to find the lattice energy. Okay, so let's write everything. So the enthalpy of sublimation, let's have sublimation, we have 150, then plus ionization energy, first ionization energy, we have 736, plus the second ionization energy, we have what? 1450, then plus enthalpy of what? Dissociation. So dissociation, we have 244. That is what we have. Then plus, then we have twice the electron what? Affinity, which is negative 348, we have over here, and then plus the lattice energy. Okay, so all we need to do over here is to make what the lattice energy the subject, and then we get our answer. So making the lattice energy that the subject, which means we add the sum of everything over here and bring it to the other side of the equal to sign. And if we do that, we are going to get negative 2526 kilojoules per mole, okay, as the lattice energy for this particular question. So this is how you use the diagram that I drew earlier to solve some of the problems for born-Haber cycle. Let's have a look at another example. Example number 2, we are to calculate what the lattice energy, same way for the following. So we are forming enthalpy of formation of what potassium chloride. So first of all, we need to draw what the born-Haber cycle, the born-Haber cycle for what potassium chloride. All right, so for potassium chloride, we need potassium, which is solid, plus chlorine, which is gas. So we need half of it to form what potassium chloride. So we have the enthalpy of what the formation over here. So we need to convert the potassium to what potassium gaseous, then we change it to what K plus gaseous. Then here we need to change this to just chlorine gas. Okay, we need to change this to just chlorine gas. So we need half the enthalpy of what dissociation, and then from here we apply electron affinity to get what Cl minus. So from K solid to K gaseous, we need the enthalpy of what sublimation. Okay, then from here to here, potassium gaseous to here, we need ionization energy. Okay, so from chlorine gas to just one chlorine gas, we need half the enthalpy of dissociation. And then from chlorine to chlorine anion, we need what electron affinity. Okay, so adding these two ions, we need what the lattice energy to form our compound. So the enthalpy of formation of potassium chloride in this example is going to be as follow. So we have, first of all, the enthalpy of sublimation plus the ionization energy of potassium plus half the enthalpy of our dissociation, okay, plus electron affinity plus lattice energy. So these are the various energies that we need to do the work. So now that we have this, let me get rid of this, and then we use that to get our answer. All right, so let me send this to the top as always. Sorry about that. All right, so we have to calculate the value for the lattice energy. So we are making lattice energy the subject. So if we make lattice energy the subject, then we have the enthalpy of formation, which is what we have over here, negative 436, then minus into bracket the sum of everything over here excluding the lattice energy. Okay, so we have the enthalpy of what sublimation, which is the same as the atomization we have over here. So we have 90 plus, then we have the ionization energy, first ionization energy, so we have 418, okay, plus then half the enthalpy of our dissociation of chlorine, which is what 242, then plus electron affinity, which is what negative. So let me just take this off and put the negative over there at once. So minus 436. Okay, so if we expand everything in the bracket over here and then we subtract it from this, we are going to get a lattice energy to be what negative 728 kilojoules per mole. Okay, so this is how we use born-Haber cycle to find the enthalpy of formation of a particular ionic compound. So first of all, you make sure you write a general equation and then you balance it to know each mole of the particular element that you need to form your product. Then you first of all convert them. If they are in their solid state, you convert them to their gaseous state, and from their gaseous state to their ionic state, depending on the charge that they are supposed to have. If it is +1, then you apply first ionization energy. If it is +2, first and second ionization energy. If it is +3, first, second, and third ionization energy, and it goes on like that. The same way, if you have the anion, you first, if it is gas, you break it down, and then you add all the necessary things, the energies you need to break them down into its gaseous state, into their gaseous form, and then you add them. Okay, and the energy needed to add them is what, the lattice energy, and then you just sum all of them and you get the enthalpy of formation of your compound. So thank you so much for watching, and I'll see you in the next video. Bye bye.